Why is it said that your memories may not be entirely real? Imagine your childhood, and those once vivid scenes. Could it be that this past, stored in your brain, is just a story that is constantly being rewritten, or even fabricated? The truth might be far more brutal, and far more wondrous, than simply having a poor memory. I hope the next 40 minutes will take you on a journey of thought, wandering between the past and the future, and ultimately reveal its stunning connection to the deepest mysteries of the universe. And behind all of this may lie a subversive way of thinking about the nature of time. Because how we perceive and store the past is itself intrinsically linked to this most fundamental dimension of the universe, time. Especially when we try to examine our own existence through the lens of memory combined with Einstein's description of spacetime, it will certainly refresh your understanding of time. To make it easier to understand, let's start dissecting from the simplest place. In daily life, time is an indispensable part. It governs our birth, aging, sickness, and death, and even the changes we observe in the world. But have you ever wondered what time really is? Is it merely a way we measure the past, present, and future, or is it something embedded within the very fabric of the universe? At first glance, time is looking at your watch, knowing it's 12 o'clock at night, and time to go to sleep. But the deeper scientists delve into the study of time, the more complex it becomes. Modern physics tells us that time is not an independent entity, something that ticks away on its own. Time is intricately linked with space. Space and time are not independent dimensions but a unified whole. Imagine space as an invisible membrane, stretching infinitely in all directions. It's not a physical film you can touch, but a smooth, serene structure that carries everything in the universe: stars, planets, galaxies, and even the light that travels between them. Now, imagine that this membrane represents not only space but also time. Together, they form what scientists call spacetime, a single, unified structure that constitutes the foundation of the universe. We usually think of space as your up, down, left, right, front, and back. Time is yesterday, today, and tomorrow. But in reality, they are not separate but are two aspects of a deeper reality, interwoven like the warp and weft of the same piece of cloth. The concept of spacetime was first proposed in the early 20th century, marking a huge turning point in how scientists understood the universe. Before that, space and time were considered separate and absolute. But then Einstein completely changed this view. In his theory of general relativity, Einstein proposed that space and time are not fixed and unchanging, but dynamic and flexible. Spacetime can stretch, compress, bend, and even ripple. It reacts to the presence of matter and energy. In fact, gravity itself is not a force in the traditional sense, but the result of spacetime being curved by mass. To understand this, imagine stretching a rubber sheet flat to represent spacetime. Place a heavy bowling ball in the center of the sheet. The sheet will bend under the weight, causing the surrounding area to curve as well. If you roll a small marble on the sheet, it will curve towards the heavier ball. This is how Einstein viewed gravity. Massive objects curve spacetime. This curvature affects not only space. Since space and time are part of the same structure, when space bends, time bends with it. This means that in Einstein's model, time does not flow at a fixed rate. There is no universal, uniform rhythm throughout the cosmos. It is shaped by the same conditions that shape space. So, in Einstein's theory of relativity, time has no built-in labels like past, present, or future. These are words we use to describe our own experiences, but they do not exist in physics itself. The equations of general relativity do not specify, this is the past, or that is the future. They merely describe how time behaves, how it stretches and bends along with space. Einstein's model treats time as a dimension, just like the 3 dimensions of space. You just need to add a 4th coordinate in spacetime, time. The 3 dimensions of space plus the 1 dimension of time together define the position and moment of something in the universe. Although in daily life it seems we can move freely in any spatial direction, and we feel we are living in the present moment and moving towards the next, in the mathematics of general relativity, all points in time seem to simply exist. The theory doesn't tell us which moment is. No. Nor does it favor the past or the future. It just presents the structure of space-time all at once. This is where it gets mind-bending. If time doesn't flow, just as all places exist in space, then all our experiences also exist in time. We experience them sequentially, but they already exist within the fabric of the universe. Einstein himself once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." He wasn't saying time isn't real, but that our experience of the passage of time might be a creation of our minds, not an inherent property of natural law. The question then is, if this is true, why do we remember the past but not the future? Why does a shattered cup stay shattered and not spontaneously reassemble? If physics doesn't favor any particular moment, why does time always feel like it's moving forward? Where does this sense of direction come from? This is the classic arrow of time problem. Although Einstein's equations treat time as just another coordinate like space, our daily experience insists that time has a clear direction. It flows from the past to the present and never reverses. We are born, we grow, we age, and eventually, we die. It's irreversible. There is a profound one-way street in the world we live in. To explain this, scientists turn to the second law of thermodynamics, entropy. Things naturally go from order to disorder, from neatness to chaos. For example, if you break an egg, the shell shatters, and the yolk runs out. This is an increase in entropy. A broken egg spontaneously jumping back into your hand and reassembling into a whole egg is extremely unlikely. It's not theoretically impossible, but the probability is so small that it simply doesn't happen in reality. This direction from order to disorder gives time its arrow. Entropy applies to everything, from stars burning out to ice melting, to the expansion of the universe. The increase in entropy gives us the feeling of before and after. It gives time its direction, even though the fundamental laws of physics themselves have no such pointer. To use a simple analogy, when you read a book, the words on page 10 are no more or less real than the words on page 50. They exist simultaneously in the book, but we read from front to back. Similarly, all moments exist in the spacetime book of the universe, but entropy causes us to experience them in one direction. When you film an egg falling and play it in reverse, it looks strange because it violates this deep rule of increasing entropy. This is why we can tell if a video is playing forwards or backward. We recognize the arrow of time. Now, things get even more fantastic. The laws of physics don't actually say an egg can't unbreak. They just say it's so improbable that it won't happen. But these equations work just as well in reverse. This means the direction of time is not intrinsic to the equations. It arises from the arrangement of things and the peculiar workings of entropy. This suggests that the rules governing the universe are more flexible. The future and the past are equally not so distant from us. But to delve deeper into these possibilities, we must ask a bigger question. If time can be bent and entropy gives a direction, is there a way to travel through it? First, let's try jumping into the future, and there are some famous successful cases. A famous case of traveling to the future due to significant time dilation from spaceflight is that of Russian cosmonaut Sergei Krikalev. In October 2005, after spending a total of 803 days, 9 hours, and 39 minutes in space over nearly 20 years, he became more than just a cosmonaut. Technically, he is a time traveler to the future. Yes, you heard that right. While on the space station, he moved at a speed of about 27,600 kilometers per hour. According to the theory of special relativity, the faster you move, the slower your time passes relative to a stationary person. So, during his 803 days in space, this difference accumulated to about 20 milliseconds. When he returned, he was technically in the future compared to if he had never left Earth. He didn't get to the future faster than us. Rather, we moved through time faster than him. This is called time dilation. It's a real effect that has been repeatedly confirmed by experiments. The equation that explains this phenomenon is the time dilation formula, derived from special relativity. We won't solve it, but we need to understand its meaning. In the formula, t is the time experienced by the moving observer, V is their velocity, T is the time experienced by the stationary observer, and C is the speed of light. When V, your speed, approaches C, the speed of light, simply put, the faster you go, the slower your time passes. Although we don't notice this effect in daily life, imagine you board a spaceship traveling at 99.9% the speed of light. To you, it feels like a year has passed, but when you return to Earth, decades have gone by. The people you knew would be old, or perhaps no longer alive. From your perspective, you've only aged 1 year, but from Earth's perspective, you've jumped into the distant future. Your own clock slowed down so much that you traveled through time without feeling anything unusual. To use a simple analogy, I watch a movie on Earth at normal speed, and you watch the same movie, but in slow motion. The longer you watch, the more out of sync you become with me. Eventually, when my movie ends, you might only be halfway through. This is what happens when you move near the speed of light. Your time flows slowly, while the rest of the universe zips by around you. Besides speed, according to general relativity, gravity is actually the curvature of spacetime itself. The more massive an object, the more it distorts the space and time around it. The closer you are to that massive object, the slower your time passes. This is called gravitational time dilation and is one of the most amazing parts of Einstein's theory. Remember in Interstellar, when Cooper pilots the ship to land on a planet orbiting near the black hole Gargantua? The gravity of this black hole stretches spacetime to an extreme degree. On this planet, compared to Earth, time almost stands still. For every hour they spent on the planet's surface, a full 7 years passed on Earth. When the crew finally returned to their ship, only a few hours had passed for them, but a crew member who stayed on the mothership had aged 23 years, simply because they were near a black hole where time flowed slowly. Although it sounds fantastical, gravitational time dilation is an observable phenomenon in everyday contexts, though its effects are far less dramatic than near a giant black hole in a movie. In the 1970s, scientists tested the effect of gravity on time by taking 2 high-precision atomic clocks to different altitudes. One clock was placed at sea level, and the other was taken to a mountaintop at an altitude of about 2,300 meters. After 11 days, comparing the 2 clocks, scientists found that the clock on the mountaintop ran slightly faster than the one at sea level. This is a direct result of gravitational time dilation. The reason is that the clock on the mountaintop is farther from the Earth's center of gravity. The higher the altitude, the weaker the gravitational field, and therefore the less distortion of spacetime. Although the difference between the 2 clocks was minuscule, only a few hundred thousandths of a second, it was measurable with the technology of the time. Besides traveling at the speed of light or near a giant black hole, there's another way to go to the future: the concept of a warp drive. In 1994, physicist Miguel Alcubierre proposed a theoretical concept called the Alcubierre drive, which caused a stir in the scientific community. Using the mathematics of general relativity, Alcubierre showed that if you could shape spacetime in the right way, you could create a region of space that moves faster than light relative to the outside universe. Inside this bubble, a traveler's time would pass normally. However, outside the bubble, the ship could cover distances in a short journey that would take light thousands of years to cross. In other words, instead of making the ship move faster and faster through space, you make the space around the ship move. Usually, when we think of travel, we think of propulsion through space, like a car on a highway. But in Einstein's general relativity, space and time are not just an empty backdrop where events happen. They are more like a stretchable fabric that can be pulled, bent, and even rippled. If you could control this fabric, you wouldn't have to move through space in the conventional way at all. You could just ride a piece of space that is itself moving. This is what we often call a warp drive. The ship creates a bubble of space around the spacecraft. In front of the bubble, space contracts, and behind the bubble, space expands. The spacecraft inside remains completely stationary relative to the surrounding space. It doesn't move at all. But the bubble itself surfs through the universe. Because the ship is not technically moving through space, it could theoretically travel faster than light without violating any physical laws. It's like surfing. You and your surfboard are still, but the wave is pushing you forward. This isn't just faster than light travel, it's also travel to the future. The reason is that time behaves differently inside the warp bubble. You might experience only a few months or years, while centuries could pass outside the bubble. Imagine leaving Earth in the year 2100 and arriving at another star after what feels like 1 year to you, only to find that Earth's calendar reads 3100. You have effectively jumped 1000 years into the future while only aging 1 year yourself. Another important detail is that you wouldn't feel any acceleration inside the warp bubble. Theoretically, you wouldn't need a huge shield to protect against interstellar dust either. You would just float peacefully while the universe outside rushes by at incredible speeds. But to actually achieve this, you would need something called negative energy, or exotic matter. This type of energy would have to behave opposite to normal mass and energy. It would produce repulsive gravity instead of attractive gravity. To date, negative energy is purely theoretical. We know it can exist in tiny amounts in quantum fields, like in the Casimir effect, but we have never been able to create or collect it in usable quantities. Although NASA's EagleWorks Laboratories is working on this idea and has conducted research, we are still very far from mastering such technology. Another idea for traveling to the future involves white holes. White holes also come from the mathematics of general relativity. They are the exact opposite of black holes, which you can only enter but never leave. A white hole is an object you can never enter because it constantly pushes everything away. Some scientists have proposed that white holes might be connected to black holes through wormholes. Leaving aside whether you could survive the journey through a black hole, you might emerge from a white hole at the other end. Due to the extreme distortion of spacetime inside a black hole, when you emerge from the white hole, you might find yourself in the distant future, far beyond the era you started in. Imagine entering a black hole in 2025 and emerging from a white hole in 4025. From your perspective, only a few minutes or hours might have passed, but thousands of years could have passed on Earth. But white holes are one-way time machines, taking you to the future without allowing you to return. However, white holes currently exist only in theory. We have captured images of black holes, but no one has ever seen a white hole. Another method of traveling to the future is to freeze yourself and wait. While it may sound funny, it seems to be the simplest way. Just sleep for a few decades, a few centuries, or even longer. When the world's technology has matured, you can be thawed and start a new life in a future era. But the current technological bottleneck is how to safely revive someone. So, whether you would survive until the day you are awakened is unknown. Although the chances of success are not high, it is an experiment of hope, more like a gamble that the future will find a way to bring you back to life. Many ways to jump to the future have been proposed. So what about going back to the past? This sounds impossible. However, when you delve into the strange world of physics, you find some signs that it might just be possible. There are many movies about going back in time, but reality is not science fiction. This is something physicists have seriously considered. Is there really a way to go back in time? Can time be treated like space, where if you find the right path, you can move not only forward but also backward? First, we must be clear that real-world concepts for returning to the past are much more difficult and complex than traveling to the future. But general relativity actually allows for some crazy possibilities. One of the most interesting ideas is the concept of wormholes, tunnels hidden in the fabric of spacetime that can connect not only distant points in space but also distant points in time. Again, Interstellar used this incredible idea, but the physics behind it is closer to real science than you might think. When Cooper fell into the black hole Gargantua, he not only experienced extreme time dilation, but he also went to a magical place. He wasn't crushed by the black hole. Instead, he ended up in a tesseract, a strange higher-dimensional space where time was no longer linear. Cooper could see all versions of the past, present, and his room, stacked like a deck of cards, spread out across dimensions. At that moment, Cooper wasn't just traveling through time, he was shaping it. And because his daughter solved the equations, future humans created the tesseract and sent him back to save humanity, a perfect closed loop across time. The entire process didn't destroy the past or create a paradox. He didn't change history in the sense of creating a new timeline. Instead, everything he did inside the Tesseract had already happened. He was always the one who sent the messages. He just didn't know it until he entered the Tesseract. The future and the past were entangled in a way that kept everything consistent. This idea aligns with a concept in physics called a closed time-like curve, where time loops back on itself and events are self-consistent. This means the future and past can influence each other without violating causality. Now you might be thinking, this isn't physically going back in time. Well, next comes the answer that physics might provide: wormholes. Theoretically, wormholes are shortcuts through spacetime. Instead of a long, flat journey through space, you could cut through a tunnel and pop out at a distant place, or perhaps even a different time. Imagine the universe is a huge piece of paper. If you fold the paper in half and poke a hole through it, two distant points touch. You can jump from one place to another in an instant. This is the basic idea of a wormhole. Physicists call it an Einstein-Rosen bridge. It's like a bridge connecting 2 points in space-time. And depending on how you set it up, it can let you travel not just through space, but also through time. Now, we are getting closer to the answer to our initial question, but things are also getting crazier. If one end of a wormhole moves through time differently than the other, it could become a real time machine. You could enter one mouth and exit the other at a different time, whether in the future or the past. One possible way is to move one mouth of the wormhole at near the speed of light, like dragging one end of the tunnel with a rocket ship. Due to special relativity, time for the moving mouth would slow down relative to the stationary mouth. When you bring them back together, the two mouths would be out of sync. Walk into the stationary mouth, and you might come out of the moving mouth in the past, and vice versa. So, what determines whether you jump to the past or the future through a wormhole? It all depends on how the two mouths are treated. If the moving mouth experiences less time because it was moving near the speed of light or stayed near a massive object like a black hole, it could be younger than the stationary mouth. Walking from the older mouth to the younger mouth would send you to the past. The reverse would shoot you into the future. Think of it like an escalator, with one side moving faster than the other. Depending on which direction you step on, you either get ahead or fall behind. In a wormhole, if you go through it the right way, you might arrive yesterday. Take the other path, and you land tomorrow. But there's a limitation. You can only go back to the moment the wormhole was first created. You can't use it to visit the age of dinosaurs unless that wormhole has been around for that long. The focus in science fiction is often on traveling forward in time because that seems easier. But going back in time is where it gets really tricky and interesting. Wormholes, at least in theory, could allow you to return to your own past and meet a younger version of yourself. Of course, there are a few huge problems. First, wormholes require something called exotic matter to stay open. Ordinary matter would collapse under gravity. Exotic matter must have a negative energy density, basically resisting the pull of gravity, and pushing outwards to prop open the tunnel. No one has ever found exotic matter, but physics allows for its existence. Quantum effects suggest that negative energy can exist. We just don't know if it can exist in the right amounts, or if it's stable enough to be used. Second, the wormhole needs to be stable. Even tiny disturbances, like radiation particles or tidal forces, could cause it to collapse before anyone could pass through. If the wormhole closed while you were halfway through, the ending would be unimaginable. At this point, paradoxes inevitably appear. If you could go back in time through a wormhole, you could do things like prevent your grandparents from meeting, or send yourself a message that changes your own decisions. Nevertheless, from a purely physics perspective, wormholes don't automatically prohibit time travel. General relativity allows for the existence of closed time-like curves, self-looping paths. This means that under the right extreme conditions, the universe might allow you to go back in time without immediately blowing up reality. If traveling through a wormhole sounds impossible for now, there's another strange idea lurking in Einstein's mathematics called a closed time-like curve, or CTC for short. CTCs are even weirder because you don't necessarily need a wormhole to create one. The very shape of spacetime itself might allow for time loops. A CTC is essentially a loop in spacetime. Time doesn't flow in a straight line but curves in a way that allows an object or person to travel forward and eventually loop back to a point in the past, forming a closed path. This means if you were to travel along a CTC, you could theoretically return to a moment in your past without violating the laws of physics, because the object or person is just returning to their original point in time through a loop, albeit with the experience of having traveled through time. This idea was first proposed by the famous mathematician Kurt Gödel in the 1940s in his model of the universe. It was a solution to Einstein's equations of general relativity, which describe how mass and energy warp spacetime. These equations allow for the possibility of closed paths in spacetime. This means it wouldn't be like the previously described time travel that goes to infinity. As a closed loop, a CTC would allow an object to trace a path through spacetime and eventually return to the moment it started, even though it has had the experience of traveling through time. Such a path would not violate the laws of relativity, but it does raise paradoxes, the most famous of which is the grandfather paradox. For a CTC to exist in reality, certain conditions must be met. First, the spacetime forming the CTC must be extremely curved or twisted. This could happen around a rotating black hole, like a curved black hole. The immense gravity around these objects could create the kind of closed time-like curves described by the equations of general relativity. Theoretically, if you entered such a black hole, you could follow the curve of spacetime and loop back to a point in time before you entered. However, this is purely theoretical. No one has actually observed this phenomenon. However, all these ideas about going back in time run into a big problem, the grandfather paradox. Imagine you build a time machine and go back to when your grandfather was young. You accidentally prevent him from meeting your grandmother. Maybe you just bump into him, causing him to miss a date. Now, if they never met, your parents would not be born. If your parents were not born, you would not be born. But if you were never born, who changed the past? Later, scientists tried to solve this problem without giving up on the dream of time travel. One idea comes from quantum mechanics, specifically the many worlds interpretation. In this view, every action you take creates a new, independent universe. So if you go back in time and stop your grandfather, you don't erase your original timeline. You just create a new timeline where you never existed. But your own timeline remains intact. It's a bit like copying a file on a computer. You don't delete the first file, you just make a new, different version. This sounds clean. The timeline you came from still exists. But the problem is, this means you can never truly change your own past. You can't fix mistakes or save people who have already passed away in your world. You only affect a copy, not your real history. Even if the many worlds interpretation helps patch up the grandfather paradox, it can't solve all the problems. There's also the bootstrap paradox, which is even stranger. Suppose you go back in time with a copy of Beethoven's symphonies and give it to a young Beethoven. He copies it and becomes famous. But where did these symphonies come from? You got them from Beethoven, but Beethoven got them from you. The original moment of creation for the music simply doesn't exist. It just loops forever in time. The bootstrap paradox messes with the basic concept of causality. Usually, something happens because something else caused it. But here, the cause and effect seem to create each other. It's like standing between two mirrors and seeing an infinite number of reflections, but you're not sure which one started it all. Scientists haven't found a satisfactory solution yet. Some believe that if time travel is possible, these closed loops are just how the universe works. Others think that perhaps these paradoxes prove that backward time travel, in any real sense, is simply impossible. Then there's the predestination paradox, an even more bizarre twist. What if everything you do to change the past actually causes it to happen? For example, you learn about a terrible disaster that will happen in the future, so you build a time machine to stop it. But when you arrive in the past, you make a mistake and accidentally cause the very disaster you wanted to prevent. You're not the hero, you're the reason it happened. Every paradox forces us to confront a stark truth. Even if physics allows for travel to the past, the way the universe is constructed might prevent you from changing anything meaningful. Maybe history is like cement. You can leave a footprint, but you can't really reshape the entire sidewalk. Or if multiple universes are real, then every trip to the past just branches off into a new world, leaving your original timeline untouched but creating countless new ones. Either way, there's no perfect solution. Every answer seems to raise more questions. Every patch creates new cracks. Time travel seems impossible for good reason. Paradoxes attack us from every corner, making the idea of going back and changing history seem like trying to unscramble an egg. The universe doesn't seem to be built for it. But if we combine all the theories, we might be able to piece together something powerful enough to bend time at will. Let's start at the core, the power source. Traveling through time isn't like driving on a highway. You're not just moving through space, you're pulling at the very fabric of spacetime, trying to fold it, twist it, and push yourself through it. This requires an unimaginable amount of energy, far beyond anything humanity has ever controlled. A rotating black hole, called a Kerr black hole, doesn't just warp itself, it drags the spacetime around it. A strange effect called frame dragging. Think of it as a giant tornado made of gravity itself. If you could somehow fly close enough without being crushed, you could ride this vortex and loop through time. The idea is that near a rotating black hole, in a region called the ergosphere, spacetime is so severely distorted that moving forward in a conventional way is no longer your only option. If you choose the right path, the right orbit, you could theoretically return to your own past. The black hole acts as a cosmic generator, a time-warping engine. Of course, in the face of such extreme energy, no known material could survive near the event horizon of a black hole. But in our hypothetical time machine system, we envision a massive space station orbiting the black hole at just the right distance. Huge magnetic fields would extract energy from plasma streams, turning chaos into something usable. Once you have the energy, you need to create the actual time channel. This is where space-time rings come into play. Imagine stirring a large bowl of honey. At first, the honey just swirls, but if you stir it fast enough, the center part starts to fold inward, forming small vortices and loops. This is what we're trying to do to spacetime itself. With immense mass and energy, we stir it so fast that it begins to fold, forming closed loops in time. These are the closed time-like curves we've discussed. The model for this idea comes from the Tipler cylinder, proposed by Frank Tipler in 1974. This hypothesis envisions an infinitely long cylinder of extremely dense matter, rotating at near the speed of light. Around this cylinder, spacetime would be so violently warped that time loops could form. Of course, there's a problem. An infinitely long cylinder doesn't exactly fit in our universe. We can't just build a never-ending spinning rod in space. So any real version would have to be finite. This makes it tricky. A finite Tipler cylinder wouldn't work perfectly on its own. You'd need extra help, like exotic matter or extreme precision during construction, to make the loops form without collapsing. In our version of the machine, we envision a giant, glowing ring, not infinite, but massive enough and spinning fast enough that the spacetime around it begins to warp. This ring would glow from the energy flowing through it, like a giant hula hoop made of starlight, spinning at super high speeds. To hold it together would require materials we don't currently have, something tougher than any metal or composite we know. Perhaps future technology could use exotic states of matter or harness the power of cosmic strings, theoretically, objects thinner than an atom but heavier than a mountain, to achieve this. It's a daunting task, but it's the scaffolding we need to shape the river of time. Even with this ring, we're not done. You still have to open a path through the warped spacetime. This is where wormholes come into play. But wormholes are unstable. To keep a wormhole open, you need exotic matter, something with a negative energy density. Negative energy, for example, is seen in the Casimir effect, where two metal plates placed extremely close together in a vacuum experience a tiny but measurable force pulling them together. This is caused by the negative energy between them. This isn't exactly the same as the exotic matter we need, but it suggests the universe might allow for its existence. If we could create or collect enough negative energy, we could inflate the throat of a wormhole to be wide enough and strong enough for a traveler, or even a spaceship, to pass through safely. But how do you know where you're going? This is where navigation becomes crucial. Ordinary GPS satellites work by sending timing signals from space. Your phone or car receives these signals, calculates the time they took to arrive, and determines your position. But in time travel, everything is moving. The Earth rotates and revolves around the Sun revolves around the Milky Way, and the Milky Way moves through the universe. If you travel just a few minutes into the future or past without accounting for these factors, you could end up floating in the empty space where the Earth used to be. The solution might be quantum entanglement. Entangled particles remain connected no matter how far apart they are. If we could entangle clocks or particles at specific spacetime coordinates, they could act as anchors, providing a way for travelers to lock onto a place and time. The work of Anton Zeilinger in quantum teleportation and Pan Janeway's experiments with quantum satellites show that quantum entanglement can be maintained over large distances. Perhaps one day, a network of quantum entanglement could serve as the ultimate map for time travelers, a network of unbreakable beacons stretching across the universe. It would be like a GPS for time, except instead of using satellites, you'd be using particles woven into the very fabric of spacetime itself. For current technology, this all seems like talk on paper. But who can guarantee that in a few hundred or a few thousand years, humans won't be able to build a time machine? A few hundred years ago, humans dreamed of flying like birds, dreamed of myths like traveling 1,000 miles in a day. But today, these have become our reality. Isn't that a miracle? Similarly, if a future civilization could master the behavior of spacetime, could build machines capable of navigating the river of time, to us now, that would be magic. Now back to our core question: how do you know your memories are all real and reliable? Based on all our previous analysis, if time travel is really achieved, then the past could be influenced by the future. This means, are those fragments of the past in your mind really as they originally were? Or have they been quietly edited? Or are they even implanted memories of things you never experienced? Alright, the mind-bending journey is over. Although time travel is filled with mysteries, pitfalls, and impossibilities, the pursuit is not without value. In trying to solve the puzzle of time, we push the limits of physics, engineering, and imagination. Human dreams are perhaps the whole point of science. In the vast universe, how can a civilization that has just entered the technological era for less than a few hundred years understand the advanced technologies that might exist in the cosmos? Just as history has shown, with enough time, humanity always has a chance to turn imagination into reality. With that curiosity and imagination, I wish you a pleasant journey into your dreams. Good night.